supervisors, Ramon and Guido. And I hope it will be interesting for you. In this project, we try to combine several different methods from different fields, some of which will be familiar for you, some of which will maybe not so familiar for you. And we combine them, I think, in a quite nice way to come up with new methods to tackle, I think, interesting and difficult problem. But let me start by motivating our work. And let's start by watching a video. So what you see here is a zebrafish larva, which has an injury, a wound here. And you see two different kinds of white blood cells. In purple, you see neutrophils, and in green, you see macrophages. And what happens in this case, so let's start to play the video. The neutrophils become recruited to the wound first and cause an inflammation. And what then happens later is that the macrophages come and chase it away. Let's maybe watch it again. So here there's only one neutrophil. It becomes chased away by the macrophage. I think it's a really cool video. But where I show it is, this is one example of some data that we have from a system of single agents moving around in space and interacting with each other in some random sense, right? And one way to model such systems is using stochastic reaction-diffusion processes. And this is, of course, only one example, right? There are many examples where we can use such stochastic reaction-diffusion models to model certain problems. The one you are all probably familiar with is systems biology, so gene expression, for example, spatial effects in protein production, ecology, population dynamics, epidemiology, so for example, modeling the spreading of a disease in a population of interacting agents. But even social sciences, so for example, the London riots from 2011 have been modeled using the stochastic reaction-diffusion process. And there are other examples like smart cities, for example, public bike sharing systems, and modeling the behavior of people sharing bikes with such public bike sharing things. And there's more and more data coming up for those type of systems, different kind of data, and there are not many methods to do inference. So what we're interested in, how can we, when we, if we have a microscopic model and some data, how can we fit our model to the data? Now let me first make more precise what kind of reaction diffusion processes I'm considering. So I'm thinking of the Doi picture. So we have point particles moving in continuous space by Brownian motion, and interactions are modeled as binary reactions, which happen with a certain rate whenever two particles are closer than a certain reaction radius of each other. Now, those models are quite nice. Yeah? They can give rise to quite complex behavior. We can simulate them, but they have many problems. First of all, analytic treatments are normally not possible, only if you have very trivial systems. And we can simulate them, but simulations become computationally extremely expensive. Right? We simulate each single particle in space performing Brownian motion and have to model the reactions explicitly. There are many simulations methods and methods to predict the behavior, but there are basically almost no inference methods to fit a data, a model to data. And that's what we are interested in here. And let me make more precise what kind of inference problem we are interested in. So for example, consider we have a cell with a nucleus, and we have a gene that produces mRNA, which diffuses and becomes translated to protein to cytosol. Now assume we have spatial measurements of the system at discrete time points. So the first time point, for example, we only measure some mRNA in blue in the nucleus. And they diffuse, and the next time point we measure some proteins which become produced in the cytosol. And we have some more measurements. And from this, we would like to do inference. So for this system, what we would like to infer? Well, the reaction parameters, right, of all of those reactions, but also the diffusion constants of the different species in the system. And maybe even some spatial properties, like for example here, if we don't observe the nucleus, we maybe would like to infer the size of the nucleus. Okay, how can we tackle the problem of inference? Well, the basic object that we would like to compute is the likelihood. So let me define the likelihood. Suppose we have some data of spatial measurements at some discrete time points, t0 to tn, and I call them model theta, so the reactions that can happen to species in the system and all the parameters. The likelihood is simply the probability to get this measurement given a certain model. So, yeah.
So, but when you say model, that includes all the parameters.
All the parameters. Yeah.
So, okay.
So if we have no measurement noise, then this is just a joint distribution, right, of the process, multiple time points. If we have no measurement noise and all species are observed, then we can factorize the likelihood because we have a Markovian system. So basically, in this case, we just have to compute all the transition probabilities from one measurement point to the next. And suppose we would want to do this by simulations. Yeah? We would, for each 2 measurement points, we would have to, by simulation, compute those transition probabilities. And the computation is super expensive, even to get one likelihood. Yeah? But to the inference, we want to have to compute the likelihood many times, right? For example, if we want to do maximum likelihood, we would want to optimize the likelihood with respect to the parameters. So we have to evaluate many, many times. And this seems just to be unfeasible to do by naive simulations. So we thought, can we come up with some clever way of doing this more efficiently? And before starting to introduce the methods, I want to give you the basic idea that we had, intuition that we had at the beginning when we started with this project. So let's look at the data again that we're considering. So we have spatial measurements at discrete time points. If you look at a single time point, then what this is just a random point pattern, right? So what we basically get is we get at discrete times random spatial point patterns, yeah, which are of course correlated in some way. And there's a class in statistics called Stochastic point processes, which does inference for exactly such type of data, yeah? For example, epidemiology. And as far as I know, there has never been a connection made between such point processes and reaction-diffusion processes. And we wondered, is there maybe a connection between the two? Because the data looks so similar. And can we use it to do inference? And the answer is, of course, yes, there's a connection, right? Otherwise, I would tell you about it. But to show you how we derived this, I will have to introduce several different methods that seem quite unrelated. So that's why I first want to give you an overview of the path that we will do, so a roadmap. So here on the right side, we have the point processes. We will in particular look at Poisson and Cox processes. And here on the left, you will see what I will be doing to treat our reaction-diffusion systems. And as I said, right, so far I think there's never been made a connection between these two. You all know the chemical master equation. We will start from that one. To go to space, we will use the reaction-diffusion master equation, which you're probably also all familiar with, right? Just a discretization of space. We will also use the Poisson representation of the chemical master equation, which maps the discrete problem, discrete particle numbers, to a continuous process. And using this one and certain approximations for certain reactions, we will apply this one to the reaction-diffusion master equation, take the continuum limit, and obtain an approximation for single time distributions of stochastic reaction-diffusion processes. And this will allow us to show that there's a connection for single time probability distributions between our reaction systems and Poisson and Cox processes. This will be our first result. Now we want to do inference for multi-time points. So we will then apply another approximation, in some sense a mean field approximation, to approximate multi-time distributions using this connection. And this will allow us to approximate data likelihoods and then very naturally to inference methods. Yeah.
So when you say you apply the continuum limit from reaction-diffusion master equation, is what you do basically approximating by SPD, or what do you mean continuum limit?
In Poisson representation space. So we will come to that later. Okay, let me start with the right side, yeah, which maybe not all of you are so familiar with Cox and Poisson processes in space. Let's start with spatial temporal Poisson processes. Or actually, well, let's start with spatial Poisson process. The spatial Poisson process is a random process on a measurable space V, which could, for example, be a subregion of a two-dimensional space. And realizations of the process are just random points in space. Random points in space. Well, this is really just a point processes, right? The Poisson process has the property that in any sub-region, the number of points is a random process that is Poisson distributed. And if we assume that the process can be characterized by intensity function, then the mean value of this Poisson distribution is just given by the integral over the intensity function. Yeah? So we can take any subregion, it's a Poisson random variable, with mean given by the integral of the intensity function. The good thing about Poisson processes, if we have some measurements d, single points si, then we know what the likelihood is. Yeah? There's just an equation where we can plug it in, and we have the likelihood. Okay, so this was a spatial Poisson process. We are interested in dynamical systems, right? So we will assume that intensity is also a function of time, and assume that for each fixed time point, we get an intensity that describes a spatial Poisson process. So we don't define a point process on the product space. We define a spatial Poisson process for fixed time points. An intensity U may, for example, be the solution of a partial differential equation. Okay, this will turn out to not be flexible enough, this type of processes. Yeah? So a possible way to generalize those processes to say that the intensity function itself is a stochastic process. What you get when you do that is a Cox process. So that's just a generalization of a Poisson process. We say U is itself a stochastic process. And given the realization of the intensity field, the process is a Poisson process. Right?
Sorry, can you go back one slide?
Yeah.
Somehow, so in other words, this likelihood, it doesn't matter, I figure out how the number of points that occur in your volume appear there. So it's just, because you can have a random number of points, but you're just saying just multiply that U of SI over whatever random number of points you have, and that's the likelihood.
Well, yeah, it just depends on the magnitude of the intensity where the points appear. Right? So if let's say the intensity is high in this corner and low here.
Yeah, I understand that. I'm just saying, I'm just trying to understand how somehow, it's just, I'm having an intuitive, yeah, but all I'm just asking is that that product is going to be over a random number of points, just.
Yeah, well, your measurements, right?
Yeah.
If you measure actual points, right? It's just the product of the measured points. Okay, for Cox process, the intensity may, for example, be given as a solution of a stochastic partial differential equation. And if we now look at distribution of points and in a certain subregion A, then this is no longer a Poisson distribution, but it's a mixture of Poisson distributions, where now the mean value, which is still given as the integral over the intensity function, has a certain distribution, right? Because the mean value itself in a certain region is now a stochastic variable. These type of processes have been used quite a lot in different fields to do inference, for example in epidemics, ecology, social sciences. The crucial point is that normally they are phenomenological models. So you don't have a microscopic description, you just empirically say you describe it by a Cox process, you do parameter inference for it, and then you use your inferred model to make predictions. That means that the parameters of your model have no real physical interpretation. They're just auxiliary parameters. And that's why they're normally considered to be distinct conceptually to stochastic reaction-diffusion processes, right? Which are mechanistic description of a given system. So let's look at a visualization of those two types of processes. So I can't really see the space here. So on the left is the stochastic reaction-diffusion process, visualized for different time points. We have particles that do Brownian diffusion, react with each other, and then some of them show up at the next time point. Some maybe vanished, some new came up, and so on. For our Poisson or Cox process, the intensity field is the state of the system that propagates in time. And conditioned on the intensity field, we get random point patterns in space. Yeah? The points don't propagate in time.
So between time points, they're independent?
Those are independent conditioned on the intensity. Yeah, exactly. But they are correlated via the intensity function.
So the points don't have any real dynamics themselves.
Yes, exactly. They just are there for one time point, and the next time we get completely new points.
So it makes no sense to view this as a movie in time.
No, no. Okay, let's come to our chemical reaction systems. Let's first start with the chemical master equation, its Poisson representation. So you're probably all familiar with the chemical master equation, but let me introduce my notation. So I will assume that we have some species xi that interact with each other with some reactions, and we have some stoichiometric coefficients. And as you all know, right, if the system is well mixed and dilute, then the dynamics can be described as a Markov jump process. And the state of the system is simply given by a vector whose entries are positive integer numbers and give the molecule numbers of the species in the system. And the single time probability distribution to be in such a state at a given time is simply covered by the chemical master equation, right? Which we will not need explicitly, but I write it down here anyway. Now, the Poisson representation is a, I think, quite nice alternative reformulation of the chemical master equation. It was developed by Gardner in 1977. What Gardner did is he made the ansatz to write a single time distribution as a Poisson mixture. So we take the solution of the master equation, write it as a product of Poissons for each species, introduce some mean variables, ui, and a mixing distribution for those variables. And it can be shown that you can always do this. And as it turns out, if we have a maximum number of two reactants and product molecules, so on all reactions on the left and the right side, not more than two different particles, then one can show that the mixing distribution fulfills the Fokker-Planck equation. Or equivalently, the auxiliary variables u fulfill the Largen equation. Yep.
But that Langevin is a new Langevin equation. It has nothing to do with...
Not the chemical Largen equation, exactly. It's a new one. Yeah. It's in Poisson representation space, right? So the variables have a new interpretation. And this is exact. So in a sense, if we could solve the Fokker-Planck equation for the mixing distribution, and plug it into this ansatz, then we get the exact solution of the chemical master equation. Just want to very quickly give you an idea of how you derive this. So you define the generating function of your distribution. When you plug this in the chemical master equation, you get a PDE for the generating function. And if you plug now the Poisson ansatz into this equation, then you arrive at the Fokker-Planck equation for the mixing distribution, or equivalently at the Largen equation for those new variables u. It looks actually very similar to the chemical Largen equation, yeah, but not quite the same. And the variables, of course, have different interpretation, right? Those are not particle numbers or concentrations, they are those mixing variables in the Poisson representation. Yeah.
This may be too technical for this talk, but if you, why do you have the upper bound of 2? Is this just to keep things non-explosive, or is that really critical?
You get higher order derivatives in your PDE. So third order derivatives, and then you have no probabilistic interpretation anymore. It can still be done. But for this to be interpreted as a probability distribution, you have to make this confinement. Yep.
I mean, again, this might not, so I mean, have you, so you have these Poisson ansatz, but I mean, we sort of know that if we have a unimolecular reactions, we can sort of always write down the probability distribution. So does that mean that you can actually solve for P of u comma T exactly for a unimolecular system, and then if you were to replace it into the Poisson ansatz, you would get the probability distribution such?
Yeah, you can do it. If you can solve for the pi, then you can do it.
You know, I'm referring to the paper by Tobias and Janke where they solve unimolecular reactions, some systems with unimolecular reactions exactly.
And I think this was for closed systems, right?
Yes.
And then you get a problem here.
multinomial solution. It's a multinomial solution.
Yeah.
Yeah, but I'm just wondering
Yeah, no, I understand.
if you can obtain that result from here.
I'm not sure, because in that case you have a conservation law, and then you get a complex valued Poisson representation. But it could maybe be done. I mean, what Gardner himself used it to prove that for open systems, in certain linear reactions, so if you have only one product particle, that you can write a solution always as a product of Poisson distributions. Yeah, and this you get directly because the Poisson representation becomes deterministic in that case, and then yeah, so you can use for that, for example.
But in general, this pi can get negative values in the general case, and U can be complex as well.
U can be complex, yeah. But depending on which Poisson representation you choose, so if you let the variables live in the whole complex plane, then pi can always be chosen
But my
positive.
question is, but because in general you may have, I mean, this gives you conditions on C. Because in general, if I give you a C, you get an evolution which is whatever you want for you. You cannot interpret it as a field or a positive field. That is what I'm saying.
In this case it works. I mean, it becomes complex valued, that's true, but if you then split it up into real and imaginary part and write it out, then you still get a well-defined diffusion process with a positive, definite, semi-definite diffusion matrix. In that case, the pi is always a positive function and can be interpreted as a probability distribution, if you let the variables become complex valued.
So pi satisfies a Fokker-Planck equation
Yeah.
with respect to the spatial variables are complex.
Yeah, exactly. Yeah. Any more questions? Okay, let's talk about the properties, which we've already covered now partially. It's an exact reformulation. I think it's really nice. It can be used for some proofs, as I just mentioned, for certain linear systems. Gardner has used it himself. But there are several difficulties, and it has not been used much. Yeah? I don't know many papers where it has been used. Yeah? One problem is complex variables. Yeah? Makes your problem difficult. You have nonlinear enlargement of Fokker-Planck equations, which you cannot solve analytically. So often it doesn't make your life any easier. Yeah? And that's why it hasn't been used much in literature. But for us, it will prove very useful. And let's look quickly at some examples. So we have a production of two particles A at the same time, and the decay reaction, then the Largen equation for the corresponding Poisson representation. We have set this, we just get the deterministic part, and we get a noise term. Yeah? Looks very similar to the chemical Largen equation, but for example, this reaction doesn't give us a noise term, yeah? So it's not the same. And if we have a production of A and a bimetal reaction, then we get such a noise term with a minus in there, yeah? So we directly see that the variables become complex valued. And let me give you an overview of different reaction types and how the Poisson representation behaves. I like this because it's quite intuitive. Yeah? So if we have, so here's the notation, just to remind you. If we have reactions of at the most one particle on both sides, then those reactions give you Poisson fluctuations, which you see in a Poisson representation being deterministic. Yeah? You just get Poisson solutions. If you allow two identical product molecules, you get super Poissonian fluctuations, which you can describe by a real mixture of Poisson distributions. And you see this, that the Poisson representation becomes stochastic, but remains real valued. If we have two different types of product molecules, then we get conservation laws there, or correlations between the two, which you cannot write anymore as a real mixture of Poisson distributions. In this we see that the Poisson representation becomes complex valued. And the same if we have bimolecular reactions. Yeah? We get sub-Poissonian fluctuations or certain correlations, so it becomes complex valued.
Sorry, so I'm not sure I'm going to refer to the right word, but I think Sam or Sauter at least will know what I'm talking about, but it don't make sense. So there's this technique for reaction diffusion models where you kind of do a second quantized field theory and you get these like complex stochastic differential equations out of that.
Mm-hmm.
Does this have any connection to that, if you know what I'm talking about?
I don't know.
What is this called? No, it's different?
It's different.
Okay.
But it's always by Dewey.
Yeah, no, okay.
It's always
Okay, I don't know if you noticed, but we saw two equations, one for Cox process and one for the Poisson representation. Sorry.
when you say deterministic, but that you mean that if you start with a Poisson,
Yes.
oh,
Yeah. You have to start with appropriate initial conditions. Yeah, we saw two equations which looked very similar, one for Cox processes and one for the Poisson representation. So as you said, the Poisson representation writes the probability of a certain number of particles in the system as a mixture of Poisson distributions. And when we looked at the number of points in a certain subregion, in the Cox process, this was a mixture of Poisson distributions. So looks very similar and suggests that there's a connection, right? We formulated the Poisson representation in non-space, right? So the next step is how do we go to space? And we do this by using the reaction-diffusion master equation, which I guess most of you will be familiar with. So what we do is we take the spatial system, we discretize it into compartments, assume well-mixed and dilute conditions in each compartment, which means that the dynamics in each compartment can be described by a chemical master equation. And diffusion between different compartments is modeled as jumps, as linear reactions. And if we now take the same species in different compartments and just treat it as a different species and relabel, then we can always write the reaction-diffusion master equation as a chemical master equation with many species, right? Which means we can just apply the Poisson representation to it. And what we then want to do is to study what happens if we take the continuum limit. And let's start by looking at a simple example. So let's say we have just above that process in a one-dimensional system, and we discretize it into compartments of length h, and ui are the Poisson representation variables. If we then look at the Largen equation, it looks like this. So it's actually a Newell equation, right? It becomes deterministic, and we get those different terms. And you see directly, this is the discretized version of the Laplace operator. So if we introduce a concentration field and rescale our parameters appropriately, we can take the continuum limit, and what we get is the equation for now a field, which is a function of continuous space, and we just get such a partial differential equation, where this is the Laplace operator. So this just describes diffusion. We get a production term and decatur. And if we now do this and look at a certain sub-region of our space and look how the probability distribution behaves, then what we will find is that the probability to find a certain number of particles in the subregion A is a Poisson distribution, and that the mean is just given by the integral over the intensity function. So it behaves exactly like a spatial Poisson process. Question?
So here, the Langevin equation that you're referring to is the Langevin equation for the Poisson representation.
Yeah.
And it happens to be deterministic here because of the taxonomy that you saw us before.
Yeah.
It
This
could
was
be that
like the first class, because we have such only one particle on both sides of the
Okay,
ratio.
so, but this, in principle, when you take the continuum limit, could be an SPD.
Exactly. If we take more general systems, we get SPDE instead of PD. Exactly. Okay, so for this simple system, we have already a connection here. Yeah, we have shown that the single-time probability distribution is exactly the same of our diffusion process, exactly the same as of a Poisson process, and we have a PDE for the intensity. But what about other reaction systems? More general ones. And as we said, for some reactions, the Poisson representation becomes complex value, right? But we want to keep a real value description. So we have to first approximate certain reactions. And I just show this on one example. Yeah? So suppose we have a bimolecular reaction. This is a propensity function. And what we now do is, yeah?
Another question. Here, exactly, you don't need only that your field is real. You need also that it's positive. So you need.
No, he needs the pi to be positive, not the u.
Yeah.
No, you as well, because you
No.
is your field. Is the field of the Cox process.
Well,
He's not.
it depends. I mean, this is just
Is the intensity.
first it's just an auxiliary variable, right? In your Poisson
Okay,
representation, and it can be negative. It's in principle no problem.
No, okay, but if U is the field of your Cox process,
Mhm.
that it must be positive.
It should be positive, yeah.
So what I'm saying is that your Langevin equation for u in the Poisson representation should preserve positivity for you.
No, because its Poisson representation refers to you integrate against pi, not against u.
But you don't use pi, you use u.
In the previous slide, his example just had somehow the u playing role of pi, but not in general.
Well, it depends how you define your Cox process. Normally, you would want a Cox process that only has positive intensities, because a negative intensity is not a generating process anymore of a spatial point pattern.
Yes, that is
But in our case, sometimes it will become negative. But for what we want to do for inference, it will not be a problem. So there will be sometimes a finite probability to get a negative
For example,
intensity.
the Cox process is always over dispersed.
Mhm.
Has always over dispersion.
Yeah.
So if you get negative values, that means that you are forcing the Cox process to describe something that is under dispersed.
It would still be over.
Should we look at some specific equation?
Fine.
Okay, so we linearize such reactions. So, for example, such a bimodal reaction by replacing the direct interaction with the interaction of the particles with the mean value of the respective other particle. Yeah? Sometimes the mean field approximation. So we replace this reaction with two linear reactions and rescale the propensities with the mean value of the respective other particle. And if you transfer this to a Poisson representation space, the larger equation will become deterministic, and we will get some expectations of now the Poisson representation variables. And so this notation is not in space, yeah. And if we go to space later, those expectations are local expectations. Yeah? We don't do any spatial aberration. So the A particle will feel the mean intensity field, local intensity field of the B particle. So there's no spatial aberration here. And although this is in some sense linearization because we get those expectations here, this is still to some extent capable of capturing nonlinear behavior, right?
So it's sort of like you're making the reaction rates time dependent through these mean fields?
Yeah.
Okay.
Exactly.
Can that lead to sort of like nonlinear PDEs?
Yep. Okay, and we do similar for all other reactions that lead to complex valued Poisson representations. And then we do the same thing as before. Yeah? We use those on the reaction-diffusion master equation, take the continuum limit, and look at what happens with the probability distribution. And by doing so, we get directly our first result, that the single-time probability distributions of certain stochastic reaction-diffusion processes are exactly the same of spatial topological Poisson or Cox processes. Yeah? For the systems where we don't have to do these approximations, right? For systems where we have to do these approximations, the same is true in approximate sense. So we can approximate the distributions by the ones of a Cox process or Poisson process. And we get an explicit stochastic partial differential equation for the intensity of the corresponding Cox process or Poisson process. And I think it's really nice, right? Those two methods have been used in quite different ways for very similar methods, and there's never been made a connection. And we find here that there's actually a quite nice connection. Yeah.
Can you say a word about what you mean by approximate in the second bullet point? Is this like a limit as the numbers of particles go to infinity?
No, I can't say when this one becomes exact. This is just because of the approximation we did on the previous slide.
And what boundary conditions do you have? What sort of boundary conditions do you have on?
That depends on how do you find your stochastic diffusion process, right? Or in your reaction-diffusion master equation, what boundary conditions you take there.
So they just inherit from there.
Yeah.
This connection is exact only when you reduce bimolecular to unimolecular.
Not for bimolecular. For bimolecular, only the second point is true.
Yes.
Yeah.
So basically, it's exact when you get rid of correlations.
Yeah. Well, it depends on the reactions. So for reactions
It is
that's where the Poisson representation is real valued, we don't have to do any approximations. So for systems that have only those types of reactions, it's exact.
Yes, but if you have a particle that goes into two different particles,
Then it's approximate.
It's approximate.
Yeah, it's not exact. Yeah.
And this equation is positively preserving, right?
That
no,
was my question.
No, now I care, because it says this is
And you
connected
see,
Cox.
yes, you see,
no,
this is my question.
for some systems, the intensity can be connected.
Oh, I see, okay, so now I have concern.
So,
Yes. But here, basically, G is just your rate functions where you have substituted U.
for some reactions, there are also expectations. Yeah, some of the reactions are replaced by expectations. Ah, you mean of the original system? No, they look a little bit different for the precise representation, but basically they look almost the same as in the chemical master equation.
Yes, the reaction that
Just
you have
the rate functions.
The rate
Yeah,
function.
exactly.
It's a very crude approximation. Crude approximation.
It's quite crude if you would want to predict the behavior of a system. I would never do this, right? But to do inference, inference is much harder to do in principle, so I think it's better to do some more crude approximations. But yeah, I would not do those approximations to predict the behavior of a system. I would never do this. But I think it's very nice, right? Because as I said in the beginning, those Cox processes are normally used phenomenologically to describe some systems where you have no microscopic description and the parameters have no interpretation. And here we get no SPDE for Cox process intensity, where the parameters have actual physical interpretation, right? We have the diffusion constants and the reaction rate constants. Which I think is already a nice connection, but as this, it's not very useful for us yet, right? Because we wanted to look at multi-time points to do inference. So what we next have to do is we have to do another approximation to get a description of multi-time points. And for that, let us go back to this picture again. We said here we have particles, right, for stochastic reaction-diffusion process that moves in space and propagate. Whereas here we have the intensity that propagates and creates point patterns. And as we said in the beginning, those points are independent between different time points, conditioned on the intensity. So this is clearly not the same. Let me skip this. But you know, we thought if we have the approximation already for single time points, why don't we do it also for multi-time points? Yeah. And let me formalize this a bit. So let's come back to the original problem. Yeah, we have some data, spatial data, discrete time points, Ti, and we would like to compute the likelihood, which, for depending on the system, we can write factorized like this. And what we now do is we replace the conditioning of the direct correlation between two different time points by marginalizing out the previous time point with respect to the intensity field at that time. So we replace the conditioning of the intensity field. But in other words, what we just do is we take the Poisson representation and treat the variables now not as auxiliary variables, but as the true state of the system. So in other words, again, we just treat it as a Cox process. And this gives us the second result, that the joint multi-time distributions of a stochastic reaction-diffusion process can be approximated in a mean field sense by the joint probability of a Poisson or Cox process. And we have an stochastic partial differential equation for the intensity field. Right? And this is really nice because this we can now use to do inference. Yeah? Because for Cox process, we know how to do inferences. So we can use methods from statistics for the first time, as far as I know, for our chemical reaction systems. In particular, the likelihood can be approximated quite straightforwardly. All we basically have to do is solve a PDE or an SPDE, yeah? Which again, we have to do approximately in some way. We do this by basis projection, but I don't want to go into detail here. And we have to do some standard filtering procedure, yeah, which I don't want to go into detail here. And this now allows us directly to inference, right? Because now we have a method to approximate the likelihood, as we wanted to do.
So when you do these mean field approximations and do inference in the mean field approximation, it seems like you're going to be inducing some bias because you're sort of you're sort of smoothing out or not directly taking into account that you're sampling from a district from the U.
Yeah, I mean, we neglect the direct correlation between the points. Yeah. So
that's not what I'm saying. I'm saying, I mean, if the U were really uniform, but I had a realization of the point process, it would be non-uniform, and I would sort of do this, to fit the U, and I don't know whether that matters from your point of view of the inference.
These are effective parameters in this case, because they correspond to the mean field solution.
I mean, we don't really fit the U field itself, right? We only fit the kinetic parameters. But the U, we do measure updates, we have measurements, and the U field will adapt. Yeah, if it's a Cox process, it will adapt to the measurements. Yeah. Which then will lead to some correlation, right? Local correlations. So it won't be just flat in that case. Yeah. But it will only approximate the correlation between different time points, right? In this mean field sense. Okay, let's look at some examples, and let's look at the example that we had at the beginning, the gene expression system. So, for simplicity, I used a one-dimensional system here, where the nucleus is on one side of the cell, and we simulate data for 30 time points, and we assume that only the protein is measured, so we don't measure the mRNA. And we perform parameter inference by maximizing the likelihood with respect to the parameters. Doing this for one set gives us one estimate of the parameters, and we did this for 100 different simulated data sets. So we get 100 estimates of the parameters, we have the mean value and the standard deviation. Yeah? This is what you see here in the table. So we have the reaction constants, dm and dp are the diffusion constants, and r is the size of the nucleus. Yeah? So we always assume that we don't see the nucleus in the normal margins. And on the top row, we see the exact value used to simulate the data, and at the bottom the inferred values. You see that the method does reasonably well. So some parameters are inferred very well, like the nucleus size, or for example, the production rate of protein. Some a bit worse, like the mRNA diffusion. But overall, I still think if we have only 30 measurement points, we only observe the protein, we have 7 parameters that are unknown quite a lot. I think this is a pretty good result. And the standard deviation is shown in the brackets, so we also get a reasonable small standard deviation.
So your likelihood here does not have any sort of mean field approximation.
It does. I mean, if we have multiple time points, we always have to do the mean field approximation.
But the other approximation is not there, right?
No, it is actually, it is, because this reaction, mRNA, goes to mRNA plus protein, gives a complex value cross representation. So we also have to approximate that one.
But it's not that binary thing you talked about. It's a different one.
Yeah.
So you have explicit, for the different parameter, usually you have the maximum likelihood in a classical theory. You write that the derivative is 0, so this gives you explicit expression of the parameter theta as a function of your data.
We can't do this here.
So how do you calculate it? You have an algorithm that
yeah, we really just do
you just run
brute force maximization on a grid. Yeah.
I'm sorry, yeah.
Just maximizing on a grid. It's looking randomly for the maximum. I mean, I will just use MATLAB fmin search to find the optimum.
How many parameters?
7 parameters.
Can you explain a bit again, sorry, what you say? So the simulated data, does it mean that you simulate one trajectory and this is your truth? You take that to be your truth?
Yes, I simulate one realization and take 30 snapshots.
Okay.
As my measurement.
And then you mentioned something about 100 realizations.
Yes, so just to get an idea of how good it is, I do the same procedure 100 times. So I assume that I have 100 data sets, and on each I do parameter inference separately, and then take the mean value to see, on average, how good our approximation is.
Okay.
Yeah.
How do you start your system in stationarity, or is there some transient elements that you allow?
In this case, we start with 0 protein, 0 mRNA, yeah, so there's a lot happening. Yeah. Otherwise, it would be much harder. We wouldn't get such good results. Yeah. Okay, but yeah, as you already pointed out, there's no Byman correction here, right? So it's a bit boring. So we want to look at an example with Byman correction. So we looked at an SRS system where we have a susceptible species that can react with an infected one and becomes infected. The infected recovers spontaneously, and the recovered becomes susceptible again. And what we did is here, we took a 2-dimensional square system and placed one infected in the corner and a lot of susceptible, and then we let the infection spread through the system. And we didn't just want to do parameter inference here, we wanted to go one step further and see if our method can do model selection. So we include an additional potential reaction, spontaneous infection reaction, and want to see if our model, our method can, from data, distinguish which is the true model. We did this using the Bayesian information criteria. So basically what we do is we take the data, and optimize the likelihood with our method, once with the additional reaction, once without, penalize the result for likelihood, and then get a comparison, right? Before looking at the results, just a picture to see what here the dynamics look like, right? We put one infected here, lots of susceptible there, and then you see the evolution at different time points. So the points here is one Brownian dynamic simulation, and the background is what our method gives us for the intensity field. So it's a superposition of the intensity fields of the three different species. So you see this wave going here through the system, which on the mean value gets captured by our method. Okay, let's look at the results. So this is a histogram telling you how often our method chose the wrong one on the left and how often the right one. And we consider both cases where the actual true system used to simulate the data did not have the spontaneous infection, and it did have the spontaneous infection. And as you can see, our method picked in the big majority of the cases the true model, and in most of the cases, I think here like more than 80, here 95% of the times, with a very strong confidence. So it's a pretty good result. So far I've only told you about accuracy, right, of those results, but what about efficiency? And for this system, for example, our method was extremely efficient. I mean, it always depends if our method corresponds to a Poisson process or a Cox process. If it's a Poisson process, extremely efficient. For Cox process, it becomes a bit slower, but it's still reasonably efficient. And here, for example, in my implementation of the Brownian dynamics simulation, to simulate one data set, one realization of the Brownian dynamics took 250 seconds. And the whole inference procedure, so optimizing the likelihood, so we have to solve the system many times, and in this case we have 4 parameters to infer, took only 10 seconds. So the whole inference procedure using our method was 1 order of magnitude faster than simulating one data set. But as I said, right, if it corresponds to Cox process, it becomes slower. Okay,
How would those scale as the system's complexity increase? In other words, would your inference time, would you expect to scale in proportion to simulation time, or faster?
Faster. I mean, depends. I mean, if you have more particles in the system, the simulation becomes slower. Our method doesn't really.
Let me say something that's a little bit less mean. I mean, so what if you just had more time points? That would not make your inference that much more expensive.
I mean, it would scale linearly.
Okay.
Yeah. But and the crucial point is more particles in the system doesn't really make it much slower in contrast to the simulation, right?
But does it depend on the dimension of the parameters? For example, if
yes, of course. If you have more parameters on infer, it becomes slower. Yeah.
If you wanted to infer, I don't know, initial condition in the system, for example,
the initial condition,
then that would have the same dimension as your system.
Well, the initial condition, I mean, we just take the first measurement as the initial condition. Just project our method on the first measurement and take this as the initial condition.
Yeah, no, but I understand that, but I'm saying if the thing that you wanted to infer from your model was where your model started, then this would have the dimension, I don't know, 200, 400 or something like that, depending on how many, or am I saying something?
You're trying to infer the initial condition?
Yeah, where the particles were in the beginning and how many particles there were or something like this.
You mean that we measure later and want to know what happened before with the first measurement point?
Yeah.
Oh, that wouldn't be a problem, actually.
But wouldn't that, I mean, essentially what I'm trying to ask in a very stupid way is, you said that it took 10 seconds, but you only had to sort of search a parameter space of dimension 4.
Yeah.
So if you had a bigger dimensional space,
then it would become slower.
Then it would become slower, and it wouldn't scale linearly to the dimension of the space.
Okay, let me summarize. So basically what we have looked at the 2 different methods, right? A stochastic reaction-diffusion process and Cox process, who have been so far considered to be conceptually distinct. And we have derived new connections between those 2, right? Which allows us to use methods from statistics for the first time for such systems. And we have used this to perform variant inference and model selection, and we found our method to be quite accurate and efficient for the studied examples. But there are, of course, lots of points where we could improve, right? We just used maximum likelihood, which is a quite naive way to do inference. So the next step would be to do maybe Bayesian inference or some more clever inference methods. And another way would be to improve the approximations we made, right? So treat Beimer corrections function accurately, for example, by letting the Poisson representation become complex and see what happens. And the same with the approximation between different time points. Yeah? So there's several possibilities to improve, but that's what we want to look at in the future. And let me finish by first thanking my two supervisors, Roman and Guido. It was really great working together with on this. I would like to thank those people for giving me a lot of input and good comments on this project. I would like to thank the ERC and the BBSSC for funding me. And if you're interested, the paper just came out 2 weeks ago. And, well, thanks to you for your attention.
So what would you care, if someone wanted to study, say, those two examples that you presented with a method that predates yours, what would be the competing method and what would be your, what would be the competing model, right? Because you're basically doing MLE on the model, right? And what would be the relative advantages or disadvantages of this Cox process representation?
I mean, first of all, I don't know many methods to do this. I mean, the ones that I know, there's discrete space and simulate the reaction-diffusion master equation. So they're super slow. So I would expect ours to be much more efficient.
On the simulation part? In other words, in the sense of, I see,
Doing the
calculating the
inference,
likelihood.
doing the inference, yeah, to approximate the likelihood. Although it would be less accurate than if you actually simulate the system, right?
But this is important if you want to do complex systems. Right?
Yeah. So I think just it would be much more efficient.
Would you mind putting up your Poisson representation that we can stare at? So thank you. Sure. Take other questions. I want to.
Well, we.
The thing where, yeah, that's good. You need to take other questions.
Okay.
So it's really nice work, I think. It's great,
Thanks.
it's great work. So the SPDEs that you have you solve them in complex arithmetic using some Orner-Maruyama method?
Well, we project them on a basis function, so we just take a finite number of spatial basis functions, project them, and then what you then get is just a finite number of SDEs.
Yeah.
And because of the approximations that we make, they're nonlinear, but the equations for the moments decouple. So in some cases, the solutions are a multivariate Gaussian, which we can just get by solving the ODEs for the mean and the variance. And sometimes we have to do additional approximations.
So if I wanted to apply your approach to semantic system with patterning like Schnoerr kinetics, it's just tri-molecular reactions. Is there any hope?
With tri-molecular reactions? Difficult. I mean, in this directly not, right? We excluded tri-molecular reactions.
That's the problem, because in that case, the Poisson representation fails. You don't have a Fokker-Grand equation.
Yeah. So, but if we linearize it in some sense again, then we could do it. Yeah.
Tri-molecular meaning 3 reactants, 3 products.
I think
Three reactants, like
three reactants.
Three reactants.
the classical Schnoerr for Turing patterns.
We would have to make an approximation again. So, in some sense, linearize again, which again would then not be able to predict Turing patterns, but to do inference, because you do a filtering procedure for the measurements, it could still work very well.
I guess, I mean, the same representation that you use could be used for the non-spatial system.
Yeah.
Are there any advantages? So let's say that you're trying to do inference using that for a non-spatial system. Is that competing with the other methods that are out there? Have you looked at this problem?
I don't see any advantage of using the Poisson representation in non-space. I thought about it, but yeah, I don't see any advantage.
But so you not seeing an advantage, not necessarily bad, but are you seeing disadvantages in using this?
Yeah, depends what you do with it. I mean, you still have a nonlinear Fokker-Planck equation if you don't do any approximations that you can't solve. if you are able to do some clever approximations there, then that might be helpful. But then you still have the Poisson kernel and you have complex variables, and I think it's tricky to use. But might be. I mean, that's one thing I also want to look into. Yeah, can we use something similar for non-spatial? But so far, I haven't found it.
I mean, you could use it, but you're not convinced that it's gonna be faster.
Some of it must be that the fact you have these diffusive connections between sort of what's going on in different cells, and that somehow has a nice representation in the Langevin form, whereas generic interactions between variables would be create some horrible terms. I'm guessing that's why this works well.
But you still have those generic reactions, right? I mean, they're just happening spatially. I guess I don't understand that. I mean, most of it will be diffusion, but don't you still have A plus B goes to C?
Yeah.
That's the part that's hard, that he has to do this
Yeah,
approximation.
I see.
But I'm saying at least it's one thing to have it like you have, you know, cell by cell, that you have to do that.
But you could do the same approximation for a non-spatial system,
Yeah,
and then
could
just see
definitely,
if
yeah.
that would work or not.
Yeah, you could definitely do that. Yeah, but
But you're saying it doesn't?
well, you can do it. The question is, how good would it be, right? I mean, it would be equally efficient, right? But I think it would be not very accurate. You know? Then I would just use the linear noise approximation and non-spatial, and just do that, and that would probably be more accurate than using this approach in non-space. But I don't know. It would be worth trying, I guess.
Another question. So some of the ion channel dynamics models, I mean, they're just examples of A goes to B, B goes to A, but they're quite complicated. You know, there might be 30 or 40 transitions. Have you looked at applying these ideas to data from those? So everything is unimolecular, so I guess you're in your Poisson space, you have a sort of deterministic representation.
Yeah.
So it would be a very simple thing to.
Yeah, that could work very well, but we haven't. But if you know how to
Yeah, no,
get at this data, I would be very
sure.
interested.
I mean, for the Cox process, you can calculate the pair correlation function. Because
The what?
the pair correlation function. And in this case, because it has always, over the dispersion is always positive, that gives you an idea of the landscape that are of your system, so the characteristic landscape. Are those in agreement with what you analyze, what you simulate?
I don't know. I haven't looked into that. But it would be probably a good idea to look at. Yeah. How well those are captured. But I don't know.
Because if you, in your near field approximation, you are ignoring, basically you are ignoring correlations. But your system, in any case, because of the dispersion, produces correlations. So I was wondering whether one compensates the other.
I mean, we don't completely ignore the correlations, right?
Sorry?
And we don't completely ignore the correlations, right?
Yes, yes, but
only to
you
some
produce
extent.
it simply because of you are superimposing
Yeah.
for some processes.
Yeah, I don't know if those would be captured.
It's kind of sort of the second round of questions, but Dave, did you get yours in?
Decided to just wait. I'll hit him up after.
So I'm half an hour slower than Sandro. So can you just explain to me, if UI is negative or complex, how do you compute Poisson of Ni given UI?
Well, I mean, that's just a function, right? And you plug it in, but it's not distribution anymore, so you couldn't sample from it anymore. But I mean,
So the likelihood, I mean, I might just be dumb here. So that's just the function which is the probability mass function with mean UI. Is that right?
well, yeah, but
And you're just saying plug that in, and who cares if it's negative or complex?
Yeah.
And you're going to maximize P with a maximum likelihood.
no. In our case, everything is real valued.
Everything what?
In our case, everything is real valued, right?
Okay. So
That's the
you
approximations that we do. Yeah. The Poisson translation, this is just an auxiliary variable, so one doesn't care. This is complex, so what? If you integrate everything out, it becomes a real valued distribution, right? So this can be done exactly. In our case, because we want to do the inference and want to make the connection to Cox process, we keep the U's real valued.
But they can be negative.
They can become negative. So.
So that term, just to be very clear, is e to the negative ui to the ni divided by ni factorial.
Yeah.
That's what it is.
That's what it is.
negative, go for it.
Yeah, even if it's complex.
That's kind of really overweight negative. Yeah.
Yeah, but
But in a formal way, you can always write something down. If you don't want
I'm
to,
not saying you can't, yeah, it's just,
Yes.
it's just interesting.
Yeah,
Yeah.
I mean, you can, the problem is that you cannot interpret pi appropriately if you
Yeah.
write it down in a formal way.
But you're saying that integral over u can be done explicitly for the cases you're looking at, and you get something that's positive.
oh no, I mean, I never use this answers explicitly. I never integrate this out because I'm not interested in this distribution really. Because what we then do is we treat the system as a Cox process. So we basically forget about this. We just say this is the intensity field of a Cox process, and for that one we know how to compute the likelihood. So I never have to integrate this into